Hello and welcome back, my dear students. In today's lesson, I'm exploring with you one of the most fascinating tools in vector calculus, which is the cross product of vectors. Unlike the dot product that we have already covered, the result of the dot product is a scalar, while for the cross product, the result will be another vector, which is perpendicular to both of the original two vectors. As we saw before with the dot product, we were able to use it in the two-dimensional space as well as the three-dimensional space. But in the cross product, this operation exists only for the three-dimensional space. So there's no other operation corresponding to the cross product in the two-dimensional space. So these are like the major differences between the dot and cross product. Both of them, they have a good number of applications. So for example, for the cross product, we can use it a lot in the real life, in physics, in calculating the torque. In engineering, they use it for normal vector, determining the normal vector to a surface. Even in computer graphics, they use it to figure out how light reflects off a 3D object. So it has really a good, promising real-life applications as a cross product of vectors. So before we start just dealing with the cross product of vectors, I need to prepare you with one tool that we needed in order to do the cross product. This tool is how to find the determinant of matrices. So basically, I'm not sure if you covered matrices before or not, but the idea of matrix is basically an array of rows and columns. We're interested, you can just have anything inside this array, but for us, we're interested in the one with real numbers. So I have it as A1, A2, B1, this is B2. Okay, so this is a 2 by 2 matrix. When I say 2 by 2, I mean it has 2 rows and 2 columns. There's 2 rows and 2 columns. So the size of this matrix is 2 by 2. We're interested in one part of the matrices, which is the determinant. We need to know how to find the determinant. In general, the concept of determinant exists only in square matrices. So when I say square matrices, I mean it has the same number of rows and columns. Okay, just like the square, length equal width. So it's available only at n equals to n times n matrices. How do we find the determinant of matrices? We multiply the terms of the main diagonal minus the subdiagonal. So I'm doing A1, B2 minus A2, B1. Just as you see here, main minus sub. It's the order is important, as you see, because the operation is subtraction, so it makes a difference. So always start left to right, main diagonal minus subdiagonal. Look at these examples of finding the determinant for 2 by 2 matrices. So if I have 2, 3, negative 1, 4, so the determinant would be 2 times 4 minus 3 times negative 1, which is basically equals to 11. If I try to find the determinant for another matrix which has a repeated row or repeated column, like this one, 4, 5, 4, 5, the determinant will be equals to 0. And this is a fact about matrices. For any matrix where we have a repeated row or column, the determinant will be equals to 0. Another case where we have the determinant equals to 0, if I have a full row or column equals to 0, then the determinant again will be equals to 0. Another fact which is really interesting about matrices, it's good to know. If I try with the first example, but I'm going to do what? I'll switch the order between the rows, let's say. So I'll switch the first row to be negative 1, 4, and the second one, 2, 3. And if I try again to find the determinant, so this will be negative 1 times 3, negative 3, minus 2 times 4, 8, so this is negative 11. So as you notice, it's exactly the same value. The only difference is a negative sign. And this is another fact about the determinant of matrices. Anytime you switch between rows and columns, you change the sign of the matrix. the determinant. So if I do two changes, it goes back to the original value. One change, it's opposite sign, okay? So here I did only one switch. So I have it as negative 11 instead of 11. So it's not necessary at this course or for the purpose of this section to be like, no need just to know a lot about matrices. We need basically the idea of determinant. So don't worry if you feel that this is the first time you hear about matrices. What I need from you just only to know how to find the determinant for 2 by 2 or 3 by 3 matrices. Now for 2 by 2, it's easy, simple. Let's see how can we find the determinant for 3 by 3 matrices. This is a determinant of size of 3 by 3, which means 3 rows, 3 columns. In general, when we try to find the determinant of 3 by 3 matrices, in general, they expand. You see this notation, what they do? They expand the matrix along either a row or a column. So maybe they expand along the first row or second row or the third one, or expand along the first column or the second or the third. So I have basically many options. Now for the purpose of this section, we're going to do the expansion only along the first row. Okay, we'll do it along the first row. You'll see why we need the first row a bit later on. Now, if I try with expansion along the first row, what will happen? I take usually the first number, okay, the first term here, which is A11. In the first row, first column, the first number, you think that you're canceling its row and column. Where do we have this term? You cancel the row, you cancel the column. What will you have? This is what will be left. So I'll take A1 times the determinant of the leftover terms after canceling the row and column where I have A1. So now it's A1, B2, B3, C2, so C3. This is 2 by 2. We already know how to find the determinant. This is the first term. Now for the second term, I'll repeat exactly the same thing, but I'll move to the second one, A2. Just think that you cancel the row and the column where you have A2. What will be left? B1, B3, C1, C3. And again, I'll repeat the same thing for the third value, for the third term. So cancel out the row and column where you have A3. What will be left? Clearly, this is what we have. B1, B2, C1, C2. Okay, so every time you start, we expand along the first row. You start with A1, cancel out the row and column where you have it, take the leftover terms. Now, I'm sure that you notice already that the middle term has a negative sign. This is coming from the idea of expansion. So this is the signs usually we use for expansion. So let's say if I'm expanding along the first row, so the first and last would remain the same. The one in the middle, I switch the sign. Expanding along the second row, they do the first one negative, positive, negative. This is the sign of A1, A2, A3. Okay, for the first row. And same thing for the second, for the third, first column. We are interested only about the first row. So what you're going to do from now on, always the middle term, switch its sign. So let's say this is a 3, you write here negative 3. This is negative 4, you write here 4. Okay, just only switch the sign of the middle term. Let's try to solve some examples with only real numbers now. Something like this. We need to find the determinant for this matrix. Okay, this is equals to. I'll start with the first number. So this is 1, even though it's 1, but I'll write it. And then the determinant of. I'll cancel out its row and column. What do I have left? You write them in order. 3, 1, negative 2, 5. Okay, I'm done with the first term. Then I'll move to the second one. Remember, for the second one, always you have to switch the sign. If it's 2, I write negative 2. And then the determinant. Cancel out the row and column. What do you have left? Negative 3, 1, 3, 5. And then I'll move to the last one, 4. Same thing. I'll take the 4, I'll cancel its row and column. So what do I have? Negative 3, 3, 3, negative 2. Now these are simple to calculate. So I have, okay, 1 doesn't affect it. I need the determinant for this matrix. So remember, we need to do what? Main diagonal minus subdiagonal. So this is 15 minus 1 times negative 2, so it's now plus 2. Negative 2. Again for this one. Negative 3 times 5, negative 15, minus a 3. The third one, third term. Negative 3 times negative 3, 6, minus 3 times 3, 9. And this is basically equals to, if you do the calculation, this one will be equals to 41. Okay, very simple. Notice that the result is what? Constant. So the determinant is always a constant term. Let's try one more. But I need you again to be careful that the middle term, we switch the sign of the middle term. So you keep it the same, no need to worry. Only the middle term. Let's try one more, just to practice more. We'll try with this one too. So this is equals to, I'll start with 4. Think, you cancel the row and column. What do you have? 5, 0, negative 3, negative 1. Second term, notice this is already negative 2. So I have to switch. It's now plus 2. Cancel the row and column where I have this negative 2. What do you have left? 3, 0, 1, negative 1. Same for the third one. Cancel row, column, so I have only these 4. So this is a 3, 5, 1, negative 3. And then the rest is simple. You do the calculation here. 5 times negative 1, negative 5, negative 0, plus 2, negative 3, negative 0, 6, negative 9, negative 5. If you do the calculation for this one, it would be equals to negative 110. So this is equals negative 110. Okay, very simple, easy how to find the determinant of 2 by 2 or 3 by 3 matrices. Now, what do we need to do all of that? Maybe you'll tell me, okay, we were working with vectors and suddenly we found ourselves just on only matrices. The next slide will show you the reason why we're dealing with determinants. The idea is here. So in order to find the result of the cross product, or sometimes they call it the vector product, of 2 vectors in the 3-dimensional space, note that this is only, again, in V3. So what I need to do for the cross product, this is the notation we're using. It's not the dot as before. From its name, it's cross. So it's A cross B. We're building a matrix to find its determinant. The first row should be the standard basis, I, J, K, in order. I, J, K. The second row should be the first one here, which is A1, A2, A3. The third row should be for B, B1, B2, B3. Okay, now to find the determinant, again, we follow the same procedure that we've done before with real numbers. Okay, we'll take I, we'll cancel row, column. We already practiced how to do that. And the order here is very important. You can't switch the order. So what we're using here, just like we're abusing the notation of determinant in order to find the cross product. Okay, let's try one like this. So I need to find the cross product for 1, 2, 3, 4, 5, 6. Okay. The first step always is to do what? We need to prepare our matrix. Remember, first row should be I, J, K, the standard basis. Then in order, 1, 2, 3, the first vector, 1, 2, 3. Then the second vector should create the third row. Now this is the matrix that we need to find its determinant. Okay, this is equals to, remember we always start the first one, I, and then cancel its row and column. So what do you have? 2, 3, 5, 6. I move to the next one. It's always now, from now on, it's negative J. Cancel its row and column. So what do you have? 1, 3, 4, 6. I'll move to the third one with canceling. So you have 1, 2, 4, 5. Now we need to find this determinant, okay? So this determinant is equals to 2 times 6, 12 minus 15, so this is negative 3. And I have an I, so this is negative 3i. I'll move to the next one. 1 times 4, 6 minus 12, it's negative 6. Times negative j, so this is plus 6j. The last one, 1 times 5, 5 minus 8, negative 3, so it's negative 3k. And this is the result. Notice that the cross product gives what? Another vector, a new one. I can write it using the standard basis like this, or I could use it just the normal vector. So you write them as negative 3, 6, negative 3. So this is the result of the cross product. Hopefully the process is easy. It's simple, just using the normal determinant, but we expand along the first row. Notice that ijk is what keeps the vector for us. So we have the result as a vector. Now, as I mentioned before, again, remember that the cross product is defined only for vectors in V3, only in the 3-dimensional space. And there's nothing similar to this operation in the 2-dimensional space. This is an important fact to remember. Now, another theorem here, it tells us that if I find the cross product for any vector times itself, the result will be the 0 vector. Notice this is A, A1, A2, A3. If I find the cross product for itself, so I'll have what? Repeated rows. And as I told you before, anytime you have repeated rows or repeated column, the determinant will be equals to 0. But this is a 0 vector, okay? It's not a 0 scalar. This is a 0 vector, so I could write it as 0, 0, 0. Now the cross product between any vector cross the 0 vector, it again will give us a 0. Why? Because I have the whole row as 0. And as I said before, if you have the whole row or the whole column as zeros, the determinant will be equals to 0. Okay, so this is like simple theorem. Now the next theorem is really interesting and it's important. We'll use it a lot, especially in 10.5. This theorem says what? For any two vectors A and B, okay, in the 3-dimensional space, their cross product is orthogonal to both A and B. So what does that mean? So if I have the two vectors A and B, their cross product is always perpendicular on both A and B. Remember, when we say orthogonal, we mean also perpendicular. So they create the angle of 90 with A and B. You can even think about it using any cube, let's say. I could use the cube to see this relation. So let's say that I have this cuboid now. So if I need to check let's say that this is the first vector and this is the second vector, okay? Then their cross product will be where? This side or this edge of the cuboid. So let's say this is vector A, this is vector B, this one perpendicular on both of them, and this is their cross product. Okay, this is their cross product. Okay, so this is important for us. So now, from now on, we know that the cross product is perpendicular on both the original vectors A and B. Now, if I need just again to use the cross product, but for what? For standard basis. So for standard basis, if I try to do the cross product for I cross J, okay, for I cross J, see, the first row is again ijk. We know that I is equal to what? Let's recall with you. So as you already know that I is basically what? 1, 0, 0. And we know that j equals to 0, 1, 0. And k equals to 0, 0, 1. Okay, these are the one we covered in section 10.2, the standard basis. So if I multiply I times j, the result will be k. Okay, notice this is 0, this is 0, only I have 1k. So this is k. we usually follow this pattern, which is easy, this cycle. So I have I, J, K. So if I multiply I times J, it will give me K. K times J, it will give me J. Sorry, K times I, it will give me J. Same thing, just you keep moving clockwise. If I go anti-clockwise, so and I say, let's say J cross K cross J, it will give me negative I. If I do J cross I, it will give me negative K, okay? So counterclockwise, just same thing. I'm following the cycle, but I'll get negative sign. Fine. Usually we use just for the cross product, okay, just as I did before. We can see them using the, I think you've heard about this before, the right-hand rule in your physics courses. So the right-hand rule usually says what? If I start with my right hand, okay, I'm using my right hand, and I align my fingers towards what? You align the fingers towards A, direction of A, and they bend the fingers toward B, okay? The fingers, we bend them towards B. Then always the thumb will be the same direction as the cross product. Okay, they're usually using just to find the forces, the resultant of the forces. So it's really important in your physics courses. Now, in general, if I just, as before, remember with the dot product, it used to be commutative property. So if I say A dot B, it's the same as B dot A, while it's not true in the cross product, okay? So A cross B is basically negative B cross A. Because if I do B cross A, that means I switch the order of one row. And as I told you before, if I switch the order for one row, that means it will be negative sign. Now, if I'm thinking about these properties, as I said before, we can just see them basically here. So A cross B is equal to negative B cross A. This is what they call now, it's not the commutative property, it's the anti-commutative property. Same thing again, if I multiply scalar with the cross product, so it makes no difference. So either you multiply the scalar with A or with B, or you keep it outside. The third one is the distributive property. So if I have A cross B plus C, so this is basically equals A cross B plus A cross C. Just only you distribute it. Same thing from the right side. Now the last two are the interesting ones that we're going to revisit again. This the fifth one says that A dot B cross C equals to what? If I change the order, the location of the bracket, and I took it with the first two, so it's now A cross B dot C. This property, what they call the scalar triple product. Why scalar triple product? Because I'm multiplying three vectors, okay? But I'm multiplying with dot product with dot B cross C. So the result will be equals to what? What do you think here? What do we get in the end? B cross C, it's a vector, and A is a vector. So if I do the dot product between two vectors, the result will be what? Scalar. That's why they call it scalar. While here I'm having three vectors with the cross product. So changing the location of the bracket, it will give this rule. So this is what they call the vector triple product. So it's A dot C, B minus A dot B, C. Anyway, we'll use the fifth one more later on in this section. Now there's a very important theorem. We saw something similar to this with the dot product. This theorem says that the magnitude of the cross product equals the magnitude of A, magnitude of B, sine of theta. Remember the relation that we covered already in the dot product, it was with cosine. So let's put them just near to each other. So the one with dot product, it was A dot B equals the magnitude of A, magnitude of B, cosine of theta. But this one is with sine. But notice, because the cross product is a vector, so they had to add the magnitude. Here, no need for the magnitude, because it's only the dot product is already scalar. Okay, so both of them. Can we use the one with sign to do just exactly as we did in 10.3 to find the angle between the two vectors? Yes, we can still use it to find the angle of two vectors, but notice that the one with the dot product is easier. So if I have the choice to find the angle between the two vectors, to use the sine or cosine, the dot product or the cross product, I'll use the dot product. It's easier, faster, but still this one works fine. Okay. See, now what do we have next? We need to have one result for this theorem. What does the result say? It says that for two non-zero vectors A, B in the three-dimensional space, these two vectors are parallel to each other if and only if their cross product equals to 0. Okay, so why do we have the cross product this time? Remember before what we covered, let's just remind you. So if I have the dot product equals to 0, it was if, and we use the double-sided arrows, right? So you know now it means if and only if. So the dot product equals to 0 means that the two vectors are perpendicular to each other. So let's say this is A, this is B. They are perpendicular to each other. Now with the cross product, it means that they are parallel to each other. From where they got this idea? Same as before, just the same technique. So if I have the magnitude of A cross B, it equals the magnitude of A, magnitude of B, sine of theta. If they are parallel to each other, we know that the angle is supposed to be what? 0 in between. So if they are parallel to each other, so A cross B will be the magnitude of A, magnitude of B, sine of 0. And this makes all of this side equals to 0. Okay, so the cross product will be basically equals to 0. So now we know the rule. This is the cross product equals to 0 means, or if and only if, that the two vectors are parallel to each other. Fine? So we need to learn these relations together. So once at the end of chapter 9, you need to know just what's the difference or what's the advantage of using the dot or the cross product. So both of them can be used to find the angle between the two vectors. Okay, the cross product has sine in its role, dot product has cosine. If the dot product equals to 0, then the two vectors are perpendicular to each other. If the cross product equals to 0, they are parallel to each other. Okay, one of the applications of the cross product is basically allow me to find the area of the parallelogram. So if I need to find the area of the parallelogram, it's basically the area of the base times the height. So if I need to find the height here in this case, so it's very simple. You think just with simple trick. So if I say that sine of theta, it equals the opposite over the hypotenuse. The hypotenuse is basically the magnitude of A. So the opposite side, which is this one, the dashed one, should be equals to what? The magnitude of A sine of theta. And this is basically the opposite sign. Let's just highlight the opposite sign, this one. Okay, now we know the height. It's the magnitude of A sine of theta. But the base is this one. Base is B. The magnitude of B. Remember, when we talk about the length of this vector, we take the magnitude. So the base is the magnitude of B. The height is the magnitude of A sine of theta. These all together, if you look at this all together, okay, so this is now magnitude of A, magnitude of B sine of theta, which is basically the cross product, right? So from now on, I can directly use the magnitude of the cross product to evaluate the area of the parallelogram. Let's say another application usually you'll see is just the area of the triangle. So if I have any triangle, okay, and I need to see it using vectors, so I'll have the same rule, but remember the triangle is basically half of this shape. So the rule, if I need to find the area of triangle, so the rule should be equals to what? With half only. Same thing, cross product, but add half to the formula. Fine, why? Because the triangle is half of the parallelogram. Okay, that's good, easy now. So we're adding up more applications to the cross product. Now see the next example. What do we have here? We need to find the area of the parallelogram with two adjacent sides formed by the vectors A and B. They give me the two vectors and they need us to find the area. Okay, let's see. So what do we know now? We know that the area is basically the magnitude of their cross product. Okay, let's find the cross product. In order to find the cross product, remember you need to build your matrix. So this is I, J, K, 1, 2, 3, 4, 5, 6. This is exactly the same question that we've done before. So their cross product should be equals to negative 3I 6J minus 3K. I could write it as a vector, as negative, the other form of the vector, negative 3. Now, for the purpose of the area, I need to find the magnitude for this vector. So the area should be the magnitude of A cross B. And this is equal square root negative 3 squared plus 6 squared plus negative 3 squared. And this is equals to square root of 54, which is approximately 348 square unit. Okay, direct, easy. Okay, now we have another application. So now we know when the two vectors are parallel to each other. We can easily find the angle in between. One important application is the area of the parallelogram or the area of the triangle, just basically the magnitude of the cross product. So the application here helps us just to find the distance between point and a line. Okay, so if I need to find the distance between point and a line, basically I mean the shortest distance. Okay, so every time if you just, anyone asks you to find the distance, so they mean basically the shortest distance. So if I have this point, okay, so I have the point, let's say Q, and I need to find the distance with the line where we have this vector passing by, so which is, let's say, PR. Okay, so if I need to find this distance, so the shortest distance should be this column. How do we find this distance? This height is again PQ. Notice here they give me points as PQR. So if I need to find the vector itself, I need to do what? PQ, the vector PQ. Usually, how do we find it? Terminal point minus initial point. So this is the vector PQ. Another vector is PR. So to find the distance, what I need to do is basically, I need to find what's PR cross PQ cross PR, which is as a cross product equals the magnitude of PQ, magnitude of PR, sine of theta. Now, if you notice here that if we look at the distance, which is this one, this is what we need to find. So this is PQ sine of theta. So this is PQ and this is sine of theta. So these two, I can replace them with what? With D. It's the distance already. So this is the distance D. Now, so finally, this equals, the cross product will be equals PR, the magnitude of PR, times the distance D. Solve this equation for D. This is the result we have. So now, from now on, this is the rule that we can use to find the distance. No need to worry again about how did we find these rules. I'm not going to ask you about the proof, but it's good to learn from where they came. So basically, this is the idea of the distance between point and a line. So it's equals the cross product of the two vectors, PQ, PR, divided by the magnitude of PR. Now let's try one example on how to find the distance here. The question says what? Find the distance from the point Q121 to the line which passes through the points P21 -3 and R2 -1 3. So basically what you need to do, you're thinking about the point Q and there's a line passing through PR. So I need to create another line, another vector with this vector, okay, in order to find what's the distance, this distance. So I have to do what? PQ. How do we find PQ? Remember, we do what? Terminal minus initial point. So it should be 1 minus 2. So this is equals to -1. Then 2 minus 1, this is 1. Same thing, 4. And I need to find, this is as a vector, okay? And I need to find PR. And this is equals R minus P. So this is 0, okay? -2 and 6. Now I need to find the cross product. You see the order of operation? I prepared PQ alone, PR alone. Now I need to do their cross product. So the cross product of PQ cross PR equals to, I need to build the matrix. So this is I, J, K. The first row is basically -1, 1, 4, as you see, the first one, and then 0, -2, 6. If I try just to do the calculation, you can easily do that, I'm sure. So the cross product will be basically 14i plus 6j plus 2k. Now what do we need? We're almost there. What I did so far, I found PQ, just only terminal minus initial. PR as a standard vector, okay? Now the cross product is ready. The only part left is just to have the magnitude for this vector. So what's the magnitude for the cross product? PQ cross PR. The magnitude will be equals to the magnitude for this one is equal radical 236, and I need the magnitude for PR as well. The magnitude of PR is radical 40. Okay, final result. Now we can easily find the distance. So according to or following to the distance formula, D will be equals to the magnitude of the cross product. So this is radical 236 divided by radical 40. This is approximately will be equals to 2.429. Okay. So this is the formula, or how can we use the cross product in order to find the distance between point and a line. Hopefully this is clear. So as you see in this section, there's few formulas you need to learn in order to be able to solve these questions. No need again to worry about the proof for these formulas, but you need to know the formula in order to use it directly. Now we have another application where we use the property number 5, as I told you before, which is the triple scalar product. Now for the triple scalar product, what we need to do is to find what C dot A cross B. Basically, if I need to do this calculation, notice what I have to do. C, let's say that ABC is A1, A2, A3, B1, B2, B3. Same thing for C, C1, C2, C3. So I need to do the dot product of C dot the cross product of A cross B. This is the matrix for the cross product, the determinant for this matrix. If I do the cross product, the dot product for these two, the result will be equals to, if you try to calculate it, so I'll have C1, C2, A2, A3, B2, B3, same thing here. If you do add them all, this is basically C1, C2, C3, A1. So this is the matrix of C, A, B. Just in order, easy one. I put the result there. You can use it directly. The parallel pipette is basically what? The three-dimensional shape for the parallelogram. If I have it in the three-dimensional space, so I have now, let's say I need three edges of this 3D shape. How do we find the volume in general? We need the area of the base times the height. The area of the base is basically the parallelogram, which is we already know. The area of the parallelogram is the magnitude of A cross B. Okay, we know the area of the base. I need the height. The height is basically, if I have the third edge here, C, and I drop it there, remember that the cross product of A cross B, AB, the cross product will be perpendicular on both of them. So this will help us in order to find the height. So if I drop this line from C into the cross product, I'll get what we already talked before in 10.3 as the component of C along the cross product. So this is what we have as the height, which is the absolute value of the component of C along A cross B. Okay, what does the component equals to? If you just recall from 10.3, this is what the component used to be. So it's A dot B over the magnitude of B. Okay, try to apply this. So now I need to apply it for this one, C along A cross B. So it's now C dot A cross B over the magnitude of A cross B. Let's go back to the previous slide. Now remember, what do we have? The cross times the component. Okay, so it's now the cross times what's the component of C along AC. That's it, it's already there. We apply it here. Cancel out A cross B with A cross B. What do you have in the end? This rule, which is C dot, which is the triple scalar product. So I have C dot A cross B. So now these are the two formulas I need you to learn. I need you to know the area of the parallelogram as the magnitude of A cross B, and the volume of the parallel pipette as C dot A cross B, where A, B, C are three edges of the parallel pipette. Fine? So we can directly use the rule. What should be one of the examples? This is a previous exam question. It says what? You need to find the volume of the parallel pipette with the edges. A, they give you three edges of the 3D shape. They give you A, B, C. So what should be the volume equals to? So as we saw that the volume should be equals to the absolute value, okay, the absolute value of C dot A cross B. And we already showed that before, that this is basically the determinant of the matrix of C and then A and then B in order. So C, what's the vector C? It's 1, there's no J, it's 0 and then 1. What's the vector A? It's negative 1, negative 1, 1. The vector B is, there's no I, so it's 0. I, the coefficient is 1, for K is negative 1. So we need to find this determinant as the volume for this parallel pipette. Okay. So this determinant will be equals to, you can easily find the determinant. So this is 1, cancel out its row and column. This is negative 1, 1, 1, negative 1. The middle term will be already 0, no need for this one. The last one will be 1, cancel the rows and column. And this is basically equals to 1. This is equals to 1. Remember, directly you'll get negative 1, but I need it with the absolute value. So this is equals to 1. So this is the volume. Okay? So that's all about section 10.4 for today. Next time we'll move to section 10.5, which is really big section. It has many important different cases that you need to learn. So for now, take care and we'll meet again with 10.5.